Once again, welcome everybody to the Economic Action Team and a replay with Dr. Elaine Ingham, Soil Food Web. And we'll get started here in a minute. And those of you who are here, thank you so much for joining. So hello everybody, welcome to our Economic Action Team. And this is a replay with Dr. Elaine Ingham, the Soil Food Web system. And today she's going to talk about how to regenerate your or wake up your soil. So get your soil working, how to bring your soil back to life, bring the soil back so that your soil works for you. Hey everybody, thank you for joining. And here we go with Soil Food Web with Dr. Elaine Ingham. Enjoy.
Hey everybody, welcome to today's amazing webinar with Elaine. Thanks so much for tuning in. We're a few minutes out from starting, but we just wanted to welcome everybody in. You know, I love these numbers going up 200 to 250 to, it's going up and up and up. But please tell us where you're coming in from. We'd love to know. You know, I'm sure this is an audience coming in from all over the world because I got your messages coming in from everywhere. But yeah, type in that chat box where you're coming from. We'd love to know. I'm out here. This office is in Berkeley. Elaine, you're coming in from Oregon right now. Awesome.
I'm in Utah currently.
Neil's in Utah. All right, here we go. Molly's coming in from Nebraska. John from Michigan. Brian from BC. Molly from Maine. Gail from Montreal. Liam from San Diego. Tereska, Montreal. Anita, Maryland. Idaho, Iowa, New Jersey. Croatia. Alberta. Jersey. Saudi Arabia. Veruca. Hey, Veruca. Good to see you here. Joseph coming in from Australia. Fanny, Montreal, fantastic. Coming from everywhere, Arizona, New Jersey, Haiti, Melbourne, New Zealand. This is awesome. It's literally every continent is represented here. This is great, seeing this many people are interested in soil biology. We had over, I think it was like 25. Go ahead.
Almost 1,000 people live last time. I think we peaked at 900.
Yeah, that was exciting. Hey there, is this, wait, Vivian, you hopping in here?
Yeah, it's Vivian.
Vivian's here too, awesome.
Yeah, I'm just gonna be, hi Elaine, and hi Neil, and hi Riley. I'll be on the back end answering questions in the comments.
Sweet.
All right, fair enough. Well, awesome, everybody. We'll get started here. How about we do that? So, Neil, why don't you introduce this whole thing that we're doing? First of all, let me know, can everybody see that presentation to the right? You should see bringing back the soil, reversing catastrophic soil issues at any scale. Neil, can you see that? Elaine, can you see the?
Yeah.
Yeah, you can see it? Okay, awesome.
Are you live?
Everyone else can see it? Vivian, what's that?
Are we live yet?
Yes, we are live. So we're going to get started right now.
We're about to start.
We are recording right now. So we are live. So, yeah.
All right. welcome everybody to Sustainable Design Masterclass's first webinar of 2018. This is our fourth or fifth with Dr. Elaine Ingham, and we've got a really good year lined up. We have the last 2 years, Raleigh and I have focused almost exclusively on agricultural related things, soil, water, agroforestry, gardening. This year we are doing a lot on water. We've got Walter Jen coming up next week, who's going to talk about restoring hydrological cycles as a way to deal with climate change. We've got Judy Schwartz lined up, who's the author of, she's the author of Cows Save the Planet and the author of, is it Hidden Water? It's something like that. And then this year, we're also going to break into some architecture-related stuff with regards to sustainability. So the other thing going on this year is Raleigh and I are going to run at least one live event coming up this spring in California. That will be focused on ocean farming. But for those of you who this is your first webinar with us, this sort of thing is what we do. Every time we put on a webinar, it's related to sustainability, agriculture, soil, water, land use, building, and we love to do it. And we've been doing it for about 2 years now. If you are on our email list, which most of you should be at this point, but if you came to us through some other way, we will send out this webinar once it is downloaded and saved and edited a little bit, and then that will be free for, I think, 4 days. All right, so it's, if you've got someone you want to send it to, if you need to leave early and you want to catch the end, you'll be able to do that as long as you're on our email list. And then you'll also get, we don't send out that many emails, but you'll also get alerts every time we're going to do a new webinar or an event. So get on that. It's on sustainabledesignmasterclass.com. I'm Neil Spagman. I'm the co-founder of this. The guy where it says Wayne Doorband is actually Raleigh Latham. He and I started this together a couple years ago, and Raleigh's going to introduce our guest today.
All right, thanks, Neil. Appreciate you showing Sustainable Design Masterclass. First of all, just double checking. It sounds like most people can see it, can see the presentation. Just give me some ones, give me some yeses, just to make sure. For those of you who have trouble with the sound, if there is no sound, just log back out and then log back in, and then that should fix your problem. So I'm saying yes, you can see the presentation. Awesome. So without further ado, here we go. Elaine, thank you so much for joining us. For those of you who don't know Elaine, she is one of those world's foremost scientists on soil biology. Before she came along, our understanding of the soil food web was close to nil. People were guessing. They had no idea what was going on beneath that microscope in the soil. Elaine has put almost 5 decades of her life into soil biology research, 45 years of life of research into the soil food web, of research into soil biology. She's been the chief scientist for the Rodale Institute. She's the founder of the Soil Food Web Incorporated and the co-founder of the Environmental Celebration Institute. To this point, she's helped thousands of people whose lives depend on the land to restore their soil biology. She's helped farmers, landscapers, ranchers. She's launched a whole movement of soil biology restoration. So I am absolutely honored to bring her on, because we need her knowledge about how to restore the soil going into the future. So go ahead, Elaine, take it away. And again, it's an honor to have you on. Oh, Elaine, I can't quite hear you at the moment.
Thank you very much, Raleigh.
Oh, now I can hear you. Okay,
enjoyed uh-oh. Now begin. Okay. Takes a little lag time there to switch over. Okay. So thank you very much, Raleigh, for that introduction. I really enjoy having the opportunity to spread knowledge about soil. And of course, we have to do this job of converting the dirt that has been produced when we do conventional agriculture. We've got to get that dirt back into the form of soil. And so bringing back the soil, we're going to be talking about new examples of where we have gone out and done conversions. And so, of course, though, we're going to do a little bit of background and make sure everybody is up to speed on what I mean by the soil food web, what I mean by converting dirt back into soil. So if I could have the next slide, Raleigh. It's up to Raleigh to do the switching. There we go. Okay. So we're going to be talking about the soil food web, and this represents the soil food web. It's kind of a who's eat who picture. It's the flow of carbon and nitrogen, phosphorus, sulfur, magnesium, all of those nutrients through this web of biology. And we need to understand what the feedback is from these microorganisms back to the plant. How do these creatures in the soil help grow plants? And so Mother Nature has been doing this system of growing plants for approximately the last 3.5 billion years on this planet. And so as rooted plants came into existence on this planet, this nutrient cycling, soil structure building, organic matter, balance, equilibrium, if you will, has been in place long before plants existed. So plants with roots have only existed on this planet for about 1 billion years. So plants didn't have to have the enzymatic abilities. They didn't have to have a nutrient cycling system because it was already happening. So the plant interacting with these organisms to help the plant make certain that they're not diseased, make certain that they are healthy. So these are all quick things that I want to quickly talk about before we go into the examples. So we always, of course, start with, let's see, I've got to turn my drawing tools on. And so starting with the sun up here, oops, I'm going to turn this into an arrow so you can see it a little bit better. So starting with the sun up here, that sunlight energy needs to be stored in some way on the planet. And so plants, of course, are the way that nature developed that production of stored carbon on our planet, that stored sunlight energy. So we can be looking at CO2 in the atmosphere with that sunlight energy from the sun through the process of photosynthesis is going to be stored. That energy is stored in the form of carbon chains. And so inside that plant, basically what we call those chains of carbons, and they can be 2 carbons long, or they can be 100 carbons long, or 1,000 carbons or more long. Exactly what form is that stored carbon? But it's available energy that everything on all the living organisms on this planet will utilize. So that plant is making stored carbon in the form of sugars, but a plant can't grow on just sugar alone. That plant requires all of the mineral nutrients that it's going to get from down here in the soil. So exactly what is that process to take the plant not available forms of nitrogen, phosphorus, sulfur, magnesium, calcium, sodium, potassium, all of that? How do you make those forms of nutrients that are in your soil at more than adequate concentrations to grow any plant you want to talk about? How do you make those nutrients available to the plant in the proper form for this plant to take up? And those nutrients need to be supplied right around the root system where that plant will be able to take those nutrients up without having to expend energy to transport those nutrients from long distances away in the soil. It doesn't work very well if the nutrients are being provided out here 6 feet, 10 feet, 100 feet away from the root system of the plant. The plant needs those nutrients offered to it right up close. And so this nutrient cycling system that was already in existence in the soil when the plants started to occur on this planet would provide that process. So what exactly is that process? Well, the plant growing these fruits also at the same time is releasing exudates out of the root system of that plant. And so, here's that a wonderful scientific term that I always figure everybody on the planet already knows this term. And of course you don't, because you haven't taken X number of years of graduate studies. And so let me define what an exudate is. An exudate is basically the sugars that this plant is making upstairs in the above ground part of the plant. So through the process of photosynthesis, the sugars are made in various sizes and lengths, and those sugars then are transported below ground, partly to grow the roots, but 50% of those exudates coming down into that root system are going to be released out into the soil in the form of sugars and proteins and carbohydrates. Well, sugars, we all know what those are, because, if you think about your kitchen, you walk into your kitchen, white sugar, brown sugar, honey, molasses, all those different forms of different kinds of sugars. And your plant's releasing some of those sugars, whatever sugar it puts out, the bacteria, so here are the bacteria down here, or the fungi, are going to be using those exudates coming out of the root system. Well, a little bit of that exudate is protein. Well, okay, what exactly is protein? Well, it's things like eggs and cheese and milk in your kitchen. So if you were making a recipe of cakes and cookies, you're going to put sugar into your bowl. You're going to put some proteins, the eggs especially, the milk, into that bowl. And you're going to put a little bit of carbohydrate. Well, what's carbohydrate in your kitchen? It's flour. So we're going to take very starchy things. We're going to take different kinds of flours. It doesn't have to be just wheat flour. It could be corn flour. It could be acorn flour, whatever you want. And you're going to put that into the bowl. And you're going to mix up that cake or cookie. So when you put this into not quite as scientific terminology, those exudates coming out of your root system are cakes and cookies. So your plant is putting out cakes and cookies to grow the bacteria, to grow the fungi that will help that plant grow better. So the plant is investing some of the photosynthate that it's making. The plant makes lots of photosynthate, so it's not really harming the plant any to give it away to the bacteria and the fungi. But those bacteria and the fungi are now told by the plant, by the kind of cake and cookie that is coming out of that root system today, or tomorrow it's different, and the next day it's going to be different. So what does the plant need? It's putting out the cake or cookie to grow the bacteria or the fungi that will make the enzymes that will go out and break down the organic matter, break down the sands, the silts, the clays, the rocks, the pebbles, the parent material, and pull out those nutrients that the plant has put the order in for. So the fungus with its enzymes breaking down those materials and then pulling into its body those nutrients. The fungus grows, but now it's elevated in concentration with respect to the nutrients that the plant wants. And of course, where are the bacteria and fungi growing? Well, it's right here next to the root system. One of the additional benefits that you get from the bacteria and fungi growing and basically covering all of the surfaces of that plant is that this is a protective layer. This is the castle wall. These are the knights in shining armor on their white chargers going to go out and do battle with the disease-causing organisms, with the things that want to harm or eat the living plant. They're going to be protected. That plant's going to be protected by these bacteria and fungi growing around the root systems of that plant. So we have to have these organisms present in our soil if we want the natural way of preventing diseases and pests to be operating in your soil. If you're seeing diseases and pests on your plants, that's a message from Mother Nature telling you that you've lost the protective layer, and you're going to need to put back those bacteria and fungi that can do that job for your plant. Well, think about the fact that your plant is an obligate aerobe. Plants can't tolerate anaerobic conditions because the toxic chemical compounds that are produced under anaerobic conditions will kill your plant, or those anaerobic conditions will cause the loss of the nitrogen and the phosphorus and the sulfur from the area around that root system, because under anaerobic conditions, those nutrients are lost as gases that blow off into the atmosphere. And of course, you can smell them. If you can smell ammonia coming from your soil, if you can smell that rotten egg smell, the hydrogen sulfide, if you can smell, or if you can go out in the middle of the night and see the phosphine gas being lost, please don't smell phosphine gas, it will kill you. So see, it's not detrimental just to your plants, it's detrimental to you and other animals. So we don't want those anaerobic conditions occurring around the root system of this plant at all. So these protective microorganisms help build structure. Bacteria put out glues that will bind the smallest particles in your soil together. Fungi grow as threads in the soil, and just like string around a bunch of packages, the fungi will bind the micro aggregates together into larger aggregates, macro aggregates, and that builds structure to allow water to infiltrate into your soil and be held in those larger pore spaces formed by the larger creatures in our soil. In addition to allowing water to infiltrate deeper into the soil, you're also going to get oxygen moving down deeper into the soil. As soon as there's space in that soil, so the airways and passageways and hallways built by the bacteria and the fungi, forming those micro and macro aggregates, the root systems can grow down deeper into the soil. Depends on exactly which plants you're growing, how deep those root systems will grow, but it's one of those things you might want to monitor and make certain that your plants are putting down their roots as deep as they possibly can go. Because if your plants do that, with all this good biology in the soil, you're not going to have to do any work at all in growing your plant. You don't have drought problems. You don't have mineral nutrient problems. You don't have diseases. You don't have pests. You don't have weeds. So is this going to benefit you as a grower of plants? Absolutely. Let these organisms do the work for you. So let's go back to nutrient cycling, because I only got partway through the nutrient cycling story, where I get off on the topic of here are all the other benefits that you get from having a good food web. The fungi and the bacteria are storing all those nutrients that their enzymes, as directed by the plant, have gone out and pulled from that soil. So we have elevated concentrations of nutrients in the fungi. We have elevated concentrations of nutrients in the bacteria. There are no organisms on this planet with higher nutrient contents than these microorganisms. So doesn't help your plant though, does it? Because all those nutrients are held in the bacteria and fungi. So how do we get the nutrients out of the bacteria and fungi and back into a form where your plants can take up the nutrients? We have to have the predators in the system. The predators of the bacteria and fungi, of course, are the protozoa. And the good guy protozoa are the flagellates and the amoebae that grow in aerobic conditions, strictly in aerobic conditions. Well, that tells you that your plant's in a good place because it's got the oxygen it needs. When the anaerobic ciliates start growing, the anaerobic protozoa, the ciliates start growing, that's when you know something's wrong. You're getting advanced notice. You can still do something about this problem before your plant dies. If you're paying attention and monitoring your soil for the presence of ciliates, how long does it take for you to monitor whether you have ciliates or not? It takes a whopping big 2 to 3 minutes to check that out. So why not be spending that time getting advance notice that something's going wrong in your soil? If all you're seeing are the good guys, then great, you don't have to worry. Start seeing those ciliates though, and you really want to do something to rebuild structure in that soil. So what caused the structure not to be there anymore? Well, nematodes. Some nematodes are bacterial feeders, and some nematodes are fungal feeders. And some nematodes are predatory nematodes. So here's the predatory nematodes up here. So we want the bacterial feeders and the fungal feeders. Of course, we don't want any of the root-feeding nematodes. Those are bad guys. But as long as your soil is aerobic, you don't get root-feeding nematodes growing in that soil to speak of. You get the beneficials. And so bacterial feeding and fungal feeding nematodes eat either bacteria or fungi. And then, of course, we have the microarthropods. The microarthropods eat the microorganisms, and in particular, fungi. That's their favorite food. And so that's who, well, just follow the arrows back to the things that these organisms eat. So why are the predators in the system going to cause the nutrients in your bacteria and fungi to be converted back into plant available forms of nutrients? Don't the microarthropods and the nematodes and the protozoa need those nutrients? But remember, I was always talking about elevated levels, much higher concentrations of nutrients in your bacteria and fungi. So when the bacteria and fungi are eaten by one of their predators, excess nutrients, way too much nutrients, are present in the bacteria and fungi for the predators to be able to contain. So these predators release nutrients in a plant available form right there at the surface of your root system. And so your plant gets the nutrients that it wants. And remember, it's not just nitrogen that's being released. It's not just phosphorus. It's not just sulfur. And so you can see one of the problems with inorganic fertilizers. We're putting on a very limited set of nutrients. It's not everything that your plant requires in the proper balances. It's huge amounts of just nitrate or just phosphate, and it imbalances. Those inorganic fertilizers imbalance your plants and sends its metabolism into crazy mode, getting way too much of one thing and not any of another thing. So your plant is going to be stressed. It's going to be unhealthy. It can't help but have these problems. Well, and then to think about what inorganic fertilizers do to your fungi, to your bacteria, to your protozoa, to your nematodes, to your microarthropods. Every inorganic fertilizer is a salt. And that salt concentration will kill these microorganisms in your soil. So as soon as you start going down the inorganic fertilizer route, you start destroying the food web. And then with none of these organisms to protect your root system, the disease-causing organisms, the pests, start attacking. And the pests and the diseases don't attack just the below ground, they move above ground. And they start causing problems above ground as well. So how do you reverse this? Get the biology back into your soil. And that's the how of that is what we're going to be demonstrating with more examples, more and more and more examples every time we have one of these, giving you more examples. And if you watch enough of these talks, you'll probably figure out the system that you need to be using for your own property. So let's go on to the next slide, if we could, Raleigh, which just lists all the benefits that we can get from having this food web properly balanced for the plant you want to grow. Now, some plants require mostly bacterial-dominated soils, not a lot of fungi. You need lots of protozoa, lots of bacterial-feeding nematodes, but maybe not so many of the fungal feeders. When we get further into succession, the more later successional plants, vegetables, row crops, we need a lot more fungi. Still bacterial dominated, but we need a lot more fungi. And I'll go through this again later in the talk today if I talk real fast. Perennial plants need fungal dominated soil. So you see there's a shift. And so we've got to match that up. And when we match that up, then you get all of these benefits where disease suppression, we've talked about that. Get the biology protecting your plant surfaces, not just your roots, above ground as well, on your fruit, on your seeds that you're growing. You need that biology. Your plant, it's gone. And now open infection court for other diseases and pests that come along. And so now you're going to have another disease. You're going to have another pest that starts to take over. So you put on more pesticide and you kill more organisms. And so you've got to put on more of those toxic chemicals. And of course, because you're applying those toxic chemicals, you're absolutely obliterating the biology that should be doing the protection. So it's kind of what I call, because you start with a little bit of toxic material and you've got to put more on. And yeah, okay, more toxic materials taking care of your problems, right? But it's leaving you with no protection. So you've got to put more of those toxic chemicals on, and then more on and more on. And isn't that the definition of a moron farmer? Because you're going down that pathway to, well, hell. The road to hell is paved with good intentions. So let's try to give the benefit of the doubt. This was done with good intentions, but where did it end us up? We've got to put this biology back into your soil. So we suppress disease. Remember, when the bacteria and fungi are being fed by the plant, they're making enzymes and they're pulling all these nutrients that their enzymes are pulling out of the organic matter in the sense of clays, rocks, and everything else. They're storing them. They're not leachable. They won't be washed away. Bacteria and fungi aren't washed out of the soil. So we retain those nutrients. And then when they're eaten by the protozoa, the nematodes, microarthropods, now those nutrients are available to your plant. These bacteria and fungi, the protozoa and nematodes, help decompose toxic materials. What if your soil does go anaerobic in some places? How are you going to get rid of those toxic compounds? Well, that takes the aerobic bacteria, fungi, protozoa, nematodes. The food web has to come along and do its job, building soil structure. So lots of benefits from having this food web in your soil. There are some other smaller corollary additional benefits that we can get from the food web, and we'll talk about them a bit as we go through some of the examples today. So the next slide, please. Now, when you go back in time and you try to figure out how did we end up going down this cute little pathway of the chemicals, the toxic chemicals destroying the biology in the soil. Well, when you do agriculture, we want to make a nice smooth seed bed. We want to have, pretty uniform surfaces. And so, back when we started doing agriculture, what you do is till. You want to put a furrow in the ground to drop your seeds into. How many times a year did people till way back when we started doing agriculture? How many times a year did they till? Well, once, to put the seed in. And, then you cover the seed over and you let the crop start to grow. And at first, in any soil, typically, if it's a good, decent soil, the first, 10, 15 years, you've got all the benefit of that good biology that's in the soil. You don't need to put on inorganic fertilizers. You don't need to put on pesticides or insecticides or any of those things. The biology in the soil is doing pretty good. But with each tillage event, even though you're only doing a little bit, you're maybe not tilling the whole thing. You're just tilling those furrows. But with each of those disturbances, you are killing organisms. Unless you're putting organic matter back in there and an inoculum of these organisms, when you get to 10 to 15, 20 years, you've done enough damage that you start to see a problem. So it takes a while, especially if you're putting organic matter back into the system. If you're leaving residues on the surface of your soil, it takes a while for the damage to become apparent. But enough disturbance for long enough, even back in the Mesopotamian times, back in Babylon and all those initial ancient civilizations, eventually they do destroy the biology in their soil. So, next slide if we could. We're going there, you're going to see accumulating over time, you begin to deplete the organic matter, and documented quite well in a number of publications. If you go to David Montgomery's book about dirt, the loss of civilization, I have his book here somewhere, I can get the right title. Well, it's a very good discussion of ancient civilization after ancient civilization, that when they started doing agriculture and they started to till and every year and not replenishing their soil, they start to see problems. Salt accumulations, loss of the organic matter, not putting back enough organic, all of these kinds of problems. Slowly but surely you lose the organisms. Can you monitor this for yourself? Can you see the effect of the tillage, of the applications of the inorganic fertilizers, of the pesticides? Of course you can. You can monitor the loss of biology in your soil, and it goes hand in hand with reductions in production. Next slide. I'm not moving on. There we go. I have to warn you a little bit in advance of when I need to have it turned. So as you have tilled and tilled and tilled at the same place for a long time, you start to build hard pans, a compaction layer that water cannot move through. You accumulate the salts that might be in your soil at that hard pan layer, and especially if you start using pesticides or inorganic fertilizers, it just accelerates this problem. But if you go back through the process of ancient civilizations, once they started to see a loss of the biology, they didn't know it was a loss of the biology, but as they lost that biology, they started putting on manures. Now, if you're collecting manure from out in the field and bringing that manure, putting it on your field that needs to be tilled, that's not so much of a problem, because you're getting all of the biology from the undisturbed areas in barns. And what do you do with the manure that is coming from the barn? That's going to be very high in salt quite often. It's going to be very anaerobic, and now you're spreading these problems out on your soil, and it accelerates the loss of the
Hey, Elaine, sorry to interrupt you real quick.
So every single ancient civilization that failed, and every one of them did, it was because they lost their ability to grow plants. If you can't feed your people.
Oh, Elaine, sorry to interrupt you. We were just having some bandwidth issues on your end. So we're going to cut your video feed, so it's just your audio.
My connection as well.
Yeah, this will make things smoother. We'll cut your video feed until maybe later in the presentation.
Yeah, cut my video feed.
Yeah, and if there's anyone in the house using internet, make sure they shut it off too. So, and close any other programs. But sorry for the little interruption, everybody. We'll get back to it right now. Elaine, can you turn off your webcam? All right.
Okay. Next slide, if you would, please.
Okay. All right. Her webcam is still on. Elaine, can you click and turn off the little webcam button below the orange arrow? You see that? Looks like a little camera. It's below the orange arrow. It's a little video camera icon.
Okay, audio connect.
All right. Sorry, everybody. Oh boy. Hold on. She accidentally switched off her audio. So let me get that turned on for her again. This is the hard part. You do a webinar and you're in a different part of the country. Some things happen. So, she got disconnected from audio. We'll get her back on, but Sorry about that, folks. And one quick thing about the Q&A. Save your questions till afterward because there's hundreds of folks here. Oh boy, Elaine, where'd you go? No. All right. Oh, here we go. All right, Elaine's audio is back on. Elaine, can we hear you? Can we hear you talk?
Okay. Yes, I can
All
hear you,
right.
and you can hear me
Awesome.
now, right? Okay. Hopefully,
Yeah, we
the
can hear
little
you great.
burp won't happen again. Okay, so just going through all of the things that destroy biology in the soil. So if I could have the next slide, please. Learning that the compaction layers in your soil is a result of doing the conventional agriculture, where without the proper biology in the soil, there is no way to build structure. So next slide, if you will. This picture here just shows where that compaction actually starts to occur, usually about 4 to 6 inches down. So why did we think that the Green Revolution worked? Because we'd already destroyed the biology in the soil. Through the tillage, the toxic chemicals, the inorganic fertilizers, we destroyed the biology in the soil. And then when you use an inorganic fertilizer, your plant can grow because you alleviate the worst limitation. But still, with the addition of just 1 or 2 different kinds of nutrients, the growth of your plant is imbalanced. It's unhealthy. It's an open infection court for diseases and pests, and that's where we go into the world of pesticides. Next slide, if you will. So, the whole problem was that we didn't monitor, we didn't understand, we had no clue what all these toxic chemicals were actually doing and exactly what were we doing to our soil. We were turning it into dirt. Next slide. So we have to learn about soil life as we can get that biology up and going. We're going to keep our nutrients in the soil. When you put on an inorganic fertilizer, it's in a soluble form. That means it dissolves in water. And as the water moves through the soil, you're going to lose all of your nutrients. 80% of the inorganic fertilizer that you add into your soil is going to be lost within the first growing season. What your plant actually comes in contact with of that inorganic fertilizer you add is going to be taken up by the plant. But because we've lost structure, we don't have a good way to deliver those nutrients they're adding in an inorganic fertilizer. 80% of everything you put on your soil is going to be lost into your groundwater, your surface waters, your drinking water. So we have to stop this. We have to stop destroying the oceans. We've got to stop destroying our rivers and lakes and streams. And so most people don't think about the problem comes from the fact that they're onto those nutrients and they wouldn't wash away. But a lot of people don't quite grasp the concept that all these different kinds of inorganic fertilizers are salts. They dissolve in water, and that's the definition of salt. It dissolves in water. It's a fertilizer, it's going to dissolve. 80% of it ends up not doing your plants any good. So let's keep going. Next slide. We've got to go back to having the organisms pull those nutrients out of the soil, those nutrients that are already present in your sands, your silts, your clays, your rocks, your pebbles. So the whole food web is required. It's not just bacteria. Don't get hung up on just bacteria. You got to have the balance with the fungi, and you have to have the predators to eat those bacteria and fungi, or you're not going to. So when somebody puts on a compost tea, and they say, well, I put compost tea on and it didn't do anything. Well, what's the probability that they didn't actually have any compost? They didn't have the whole food web. Yeah. So you got to be checking. You got to know that what is in the soil, what's missing in the soil, and make certain that you're adding it back. Next slide, please. So all the mineral nutrients that your plant needs is already in the soil. Why would you need to add more? Well, a lot of people go, well, where's your data to show that my soil has all the nutrients that it needs? Because we're talking about total nutrients here, not just some industry test into a laboratory for a chemical analysis of your soil. They are not telling you about 90% of the nutrients that are present in your soil. They only tell you about the soluble nutrients. And in the case of 4 nutrients, they'll tell you what's in the exchangeable and soluble forms. So base saturation is giving you probably about 10% of the total nutrient pool. When you're looking at your soluble chemical information in that soil chemistry test, you're only looking at less than 1% of what's actually available, could be turned into an available form in your soil. Next slide. I think we'll bring up the table showing total nutrients present in your soil. Can I have the next slide? Hello? Raleigh?
Yeah, I'm seeing organisms do all the work in the soil. What do you see? Hello?
Next slide.
Which one do you want? Do you want the organisms do all the work in the soil, or the hold on, sorry folks, or the minerals in the soil? Hello, Elaine.
I need so you've advanced it and it's not coming through on my screen.
Oh, you don't see it? Is it do you see minerals in the soil? Because that's where I'm on right now.
There we go.
Okay, great.
Okay, now I've got organisms do all the work in the soil, and there we go. That's what I want, the minerals in the soil. So when we're looking at mineral nutrients in the soil, people will often say, well, no, my soil chemistry test tells me that I've got 1 part per million nitrogen, or I've got half a 2.5 parts per million of phosphate. Well, you're only being told about the soluble nutrients in your soil. This table shows you total nutrients. And this particular table, Sparks 2003 published, where he went around the world looking at soils all over the planet, doing total nutrient concentrations. And so the median in that second column, I think my little purple, there we go, it's still there, that average or median value for any one of these nutrients. So, go down the left-hand column, oxygen, silica, aluminum, iron, there's carbon, calcium, magnesium. Let's go find our nitrogen. There's nitrogen. Oops, nitrogen, that's nickel I pointed to. Nitrogen, when you're looking at nitrogen, on average, in general, any soil on this planet has 2,000 parts per million nitrogen. Oh, you only need 1 or 2 parts per million in order to grow a plant. And your soils actually are containing per teaspoon 2,000. Now, there is some variability as you go from different soils. Some soils have nitrogen concentrations up at 5,000. Some are only at 200. Well, that's more than enough. In any soil on this planet, there's more than enough nutrient to grow plants. But these are not plant available. You have to have the biology in your soil in order to pull those nutrients out and convert them to a plant available form. So this is why we have to have the food web present in our soil. So if I could have the next slide. Organisms do all the work. So the next slide. There's always lots of different ways to say the kind of same information. We've seen this before, so let's pop to the next slide. Right biology enhances all these beneficial things. And now going on to how the soil food web reverses these common problems that we've already touched. You start looking at a field that has been treated in this fashion, big equipment out on the soil when the soil's wet. You're asking for a horrific compaction problem. In order to hold those big pieces of equipment from sinking into the soil, you have to have a compaction layer. Well, what I would like to see here, instead of bare soil, let's get a permanent low-growing plant cover on this soil, so we never have bare soil. When you look at this field and you look at the green plants that are growing in here, what are those? Those are weeds. Those are obnoxious and difficult to get rid of and will definitely compete with your plant. So another aspect of what these weeds do is keep the soil in a bacterial dominated mode. And if you're trying to grow a vegetable or a row crop, your plants are going to be harmed because you don't have enough fungi in here. So how do we keep the proper balance through the whole year? How do we prevent your equipment, when you get out there and start driving around on your soil, from causing this kind of compaction? Well, you need to have that permanent cover. So compaction, what causes it? I think you got that figured out. What causes compaction? What does compaction affect? Your roots can't grow down deeper than that compaction layer because of the anaerobic conditions occurring in that compacted layer. Those toxic anaerobic waste compounds will kill the roots trying to grow into that compacted zone. The compacted zone is where the diseases and the pests are hanging out and having a party. That's where they're concentrated. If your roots can somehow push their way into that compacted soil, they're going to get whammied by this huge concentration of disease-causing organisms. There's no oxygen. You can't get oxygen to move through that area. We have to break up that compaction layer. So for the last time ever, you're going to go out and till your soil. You might as well get a penetrometer, test and figure out where all your compaction layers, where all your hard pans are. Find out where they are and make sure that you're going to use tillage equipment that will break up all those compaction layers down to 4 feet. Then last time ever, you're going to go in and till your soil. And so you put a layer of compost on the surface. So right in front of your tillage equipment, you're blowing out a good layer of compost, a ton of compost, really good compost with all the right organisms. You're throwing that layer of compost out at a mere dusting, but that's okay. We just need an inoculum. We don't have to put in all the organisms that we need. We just have to put in a seed, basically, an inoculum of all the organisms that we need, and then they will start growing. We're going to have to make sure there's food in there, but hopefully the roots from last year's crops, the residues from last year's crops that you're going to till in will do the trick. So you till that in, and you start building structure. You start building the disease suppression. You start, all the good things start to happen. Now, this particular picture reminds me to talk about surface compaction, because that's caused by a little bit different problem than big equipment or lots of people walking across something. In this instance, when water is pulled up through your soil in the summertime, because it's very dry, evaporation is occurring off the surface of your soil, the water is pulled upwards through your soil, and all the salts that were in that water, as it evaporates, the water goes away, but the salts are left behind. And so this kind of compaction layer is an extremely high salt environment. And if you put your seeds on top of this, that salt will kill the seed. You can't get germination, it won't grow. So this is that surface compaction where the soil surface turns into concrete. This is, in this picture, It's just a pretty thin layer at the surface of the soil. But as you don't do the proper things to get rid of this over the years, this compaction layer gets deeper and deeper and deeper until you get a good, 2 to 3 or 4 or 5 or 6 inches of concrete at the surface of your soil. Because as evaporation is gone, you lose the salt, you lose the water, but you don't lose the salt, and it concentrates at the surface. How do you deal with that? Well, it's putting really good organic matter in there and then making sure that you put an inoculum of these organisms. So a good layer of mulch, maybe you have to till that in one last time. You're going to have to till, and then you will never till again. And then you put the organisms on as an extract or as a tea. So next slide, Raleigh. Yep, go. This is a good example of the kinds of situations we see over and over again. Where's the compaction layer in this picture? So if you're trying to figure that out, it's right here. How was that compaction layer formed? How did that occur? Well, two things caused this. The original farmer that farmed this land was putting in this hard pan, in this compaction layer, because of the tillage equipment that he was using. He was losing productivity. He couldn't pay his taxes, so he sold this land to a housing development. We're on the edge of the city of Boston. And so in comes the construction company. And as they drive all their big equipment out here, they are by law required to compact the soil around the house so that the foundation will go in. So, we're not talking about compacting it to 1,000 psi, but there are certain state laws that require that you compact the soil so your foundation doesn't move. So that causes, several things causing that compaction layer. Look at what happens to the root systems. The roots from this tree, the roots from the grass, the roots from the trees and shrubs around were constrained. They couldn't grow down through that compaction layer. So all of these roots, instead of going down where they should, deeper and deeper and deeper into that soil, they hit that compaction layer right there. The roots are killed. So these plants have no choice but to go sideways. And so the roots start growing out sideways. The roots from that shrub are fighting with the roots from that tree. They're fighting with the grass. They're fighting with these shrubs over here. And so none of the plants are healthy. All of them are sick. All of them have problems. How are we going to fix the health of these plants? How do we get food that's nutritious? We've got to break up that compaction layer. So make certain that you have really good biology in your mulch layer that you might have on top of your soil. Or if you don't have a good mulch layer, go buy some good mulch, inoculate it with the proper biology, and then for the last time, you're going to mix that material into the soil. In the case of a perennial, you're not going to be mixing that soil right next to the base of the tree. You're going to go out to the edge of its root system. And maybe, because here we don't have any place that doesn't have plants and doesn't have perennials already in there, we would inject the compost all the way down through all of the compaction layers that are here. We would inject all the way through, inoculate that soil with the compost extract or compost tea, all the way up to that profile. We would spray it out of our injector, put a good dose up here on the surface so that we're sure we're putting as much biology all the way through that soil. So every 3 to 5 feet, you would want to be putting in an injection point so that you would cover all of the property and rebuild structure in all of these places so the roots will go down. How far can the roots of that tree go down? How far down do the roots of the grasses go? How far down do the roots of those bushes go? Well, that tree, this particular variety, ought to be going down at least 100 feet. The shrubs should be going down 50, 60 feet. The grasses should be going down 15, 25 feet. So you can see all of these plants are severely compromised because of the damage done to this soil. So we have to fix that. Next slide. How far down can root systems go? You can go as, here's an example of a grass planted by Hendrika Schraven in really good, well-structured soil. The seeds were put in July. And in July, germinated, started growing. It was mowed just before this. We dug a great big PVC pipe going down through the soil, pulled out with big equipment, took the PVC pipe off, washed that root system. And so you can see that in 3 months, the root system of this grass in healthy soil goes down a full 4.5 feet. By the time this plant is a year, 2 years old, this root system should be down at 15 to maybe 25 feet. Do you have to worry about drought? No. Do you have to worry about weeds? No. You have to worry about, do you have adequate biology to maintain this type of growth? So some of the tools that we need to be using. So keep going, next slide. When we look at weeds, these are some results of weeds, where one of my favorite ways to do this is to split my field in half. And at half of the field, we just maintain the chemical applications, the toxic biology, the conventional system, no added biology. We're adding the same amount of carbon, we're adding the same amount of nitrogen with and without biology, but this one side has no added biology, the other side has the biology. And then we go through and we weed everything. So there are no weeds on either the no biology or the plus biology. And then we stop weeding for the next 2 weeks. And we come back in after 2 weeks and we measure the amount of time that it takes for us to weed the no biology side as compared to the plus biology side. And so when you look at these data, it's taking 30 minutes as compared to 5. It's taking 45 minutes as compared to 10 minutes. It's look down at the kale. What kind of soil do you want? Something where the weeds are taking over and burying your kale. We couldn't even find the kale plants in most instances after 2 weeks. Whereas on the no biology side, no weeds to speak of. I think there were 3 weeds, and so we give the lowest value we can. So all the benefits. Next slide. Trying to get to my examples. So here's an example of a situation where here's in a grape vineyard. We had a vineyard that had lost all of the grapes early in the spring due to a late frost. So they weren't going to be growing any grapes, so they allowed us to come in and cover everything in this vineyard so that we had 70% coverage with the disease-causing fungus called Botrytis cinerea, black spot. And everything was covered, so we knew everything was going to become diseased if we didn't do something about it. So we had a section where we just applied water to the plants, and we showed, what's the result of not having any control at all when we make certain that the disease is there. The next section of that vineyard, we applied 10% biology on the leaf surfaces. Was that adequate? We put 50% into the next section, 70% coverage in the next section, 100% coverage in the last section. And so what I want
Did everyone else just lose Elaine? Everyone else just lose Elaine? Everyone else just lose Elaine? Everyone else just lose Elaine?
Hey, Elaine, for some reason I got,
Raleigh,
hey,
the
sorry, I
whole
got
thing.
kicked out for some
Too,
reason.
I got kicked out too. The whole thing dropped out.
Yeah, okay. Well, luckily people are trying to log back in. God damn it. I'm not sure what the hell happened there. Okay, hopefully we'll be able to resurrect this thing. All right, Elaine's coming back in.
What just
Sorry,
happened, Raleigh?
everybody. I'm not sure. It just kicked everyone out. It said some other organizers in, and then everyone got kicked out. We will not use this software in the future. God damn it. All right, well, luckily she's hopping back in. Sorry, everybody. That's really lame. All right, who is in the staff here? Okay, for some reason.
Yeah, I got kicked out too, Raleigh.
I think everyone
Yeah.
got kicked.
Yeah, okay. All right, the
You
thing
gotta
is,
check out who.
sorry, everybody, we're gonna get back to it. Can everyone hear? All right, you didn't get kicked out. It said switch to Zoom in the future. Yeah, for sure. Okay, can everyone? All right, everyone's hearing. We're gonna kind of. All right, we still didn't lose, folks. We're gonna see if we can resurrect this presentation. We're good. All right, so now let's get back to it. We're gonna get Elaine back in on here. Well, she's gonna see. I was a little bit pissed. I threw my pen across the room. It was going so good. All right. As soon as Elaine gets back in, we'll start this again. All right. Hold on. I gotta give Skype Elaine a little Skype ring and tell her to log back in. Elaine, are you back in here? Can you hear us, Elaine? Elaine. Sorry about that, folks. We'll get right back into it. Okay. Hey, Elaine. So
Hey,
we got the presentation back up. Are you there? Hello?
I can hear you. Can you hear me?
Uh,
What went wrong? Something went wrong?
okay.
Hello? Hello?
Hey, Elaine. Okay, so you just need to click the log. Oh, she's back. Okay, great. I'll get off my Skype.
Okay.
All right. Oh, well. Okay, Elaine, can you see the screen?
The screen right now has a picture of a mountain and a lake on it.
Okay, so let me switch this back. Give me 1 sec. I just need to get this presentation back up. Okay, can you see the diseases are outcompeted
Yep.
screen now?
Yep. There we go. Got it.
All right, everybody, we're back to it. We only lost 50 people, but it's all good. Thanks for sticking around through our crazy, crazy errors. Hopefully that didn't screw with the recording at all. So yeah, sorry,
I'm
Elaine.
sorry. Yep. So I'm real sorry about that. I don't quite know what happened, but this example with the grapes, we're looking at the 50% leaf coverage. You can see that if we don't have adequate coverage with the biology on the leaf surfaces, that the diseases will take off and cause problems. So the 0, the 10% coverage, the 50% coverage, we lost all of the leaves on the plants. 70% coverage, 100%, absolutely no disease that we can find at all. So when you're dealing with these kinds of problems, we need to be making certain that the biology is covering these leaf surfaces adequately. And the way we have to test that is to look at your compost, extract your compost tea going onto these leaf surfaces. It would be a tea. We just want to make certain that we have adequate numbers of bacteria and fungi in that compost tea that you're applying. If you don't have adequate biology, don't bother applying it. Putting water out onto the surfaces of these plants isn't going to do anything to prevent the growth of the diseases and the pests and problems. Okay, so next slide. Examples of where we've been doing things to bring plant and soil health back. This is work we were doing in South Africa. So when you're looking at this, these comparisons, it's on the left-hand side, we're looking at the system that had just the chemical applications. This is conventional agriculture. And you can see the whole bottom part of these tomato plants have just been completely wiped out with disease. And actually the major problem here are root-feeding nematodes in the soil attacking the root system. So the plant can try to keep growing, and you can see the upper part of that plant is still, it's got blossoms on it, it's got tomatoes, but production has been severely limited. So not going to see the kind of growth that you want. How do you deal with this? Well, we put compost in the furrow where the starts of the tomatoes are dropped in. We make certain that in the potting mix for those starts, we've got really good biology. We either drench them with an extract of compost, or our potting mix can actually be 100% compost, maybe a little bit of vermiculite to give good fluff. But what's put into the ground has the proper biology. We also then typically, in the after example, where we actually have put the biology in, we applied 3 applications of compost tea to these plants as they were growing. So one at the first application of compost tea at the first true leaf stage. And of course, when you're spraying the true leaves for the first true leaves, then you're going to get the soil too. And about a month later, so if you go to look, think about the height of the plant. The 1 month, the plant is typically a certain height, and so you're going to be applying that. And then by the time a month later, the tomatoes are starting to blossom, and then you can see the growth continues. Notice that the plants in the after side are a little bit shorter than the plants in the before side, because you got to remember this plant is trying to escape the disease. It's trying to escape the problem. So all of this area, they've lost production, and the plant now is growing taller and taller. But the production, the tomatoes produced, are significantly less. So shorter plant, but stronger stalk, stronger branches, growing the same amount of tomatoes. Actually, we about tripled yields here, if I remember correctly. So an example of how we get the biology into the soil in the first growing season and start to see this improvement right away. Next slide. So we're looking at Komodo dragons here. This is some work at Woodland Park Zoo, which is up, I believe, in, I can never remember, it's either Portland or Seattle, Washington. And with the Komodo dragons, these are interesting creatures. They are from tropical systems. They are very neat and tidy animals. They have a latrine. And so all of the animals in this area will poop and pee in one place. Well, you can imagine that that gets pretty disgusting rather rapidly. And so in the park, in the zoo, they had to send people in every week to clean out all of that area, remove all of the fecal material, all of the wet sand from the urine, pull it out of the cage, and then come back in with sand and put all the sand back into the latrine. And they had to do that every week to keep the diseases and the flies and things like that down. So they asked us, when they listened to one of my talks, they asked if they used a compost extract or a compost tea, could they actually do some decomposition of that material in the cage? Did they have to come in and replace every week? Could they lengthen the time? If they could just come in every other week, that would have reduced their costs by half. And imagine as a human being walking into the cage, making sure that the Komodos are all in the other part of the cage. So because if you've ever been bitten by a Komodo dragon, you realize some of the most horrible bacteria on this planet live in their mouths. If you're bitten by a Komodo dragon, you are probably going to lose that limb due to the gangrene that results. So you want to be careful with these guys. So who's going to undertake this job? And how much are you going to be paid for it? Yeah, this is hazard pay. And it's not a very pleasant job. So if they didn't have to send somebody in here every week, they were going to just be over the moon about the reduction in the costs. So the experiment that we did was to put the compost tea through the irrigation system. These are tropical animals. They, it typically rains every day. The temperature in here is kept up around 85 to 90 degrees. Can you imagine having to be in a moon suit to walk into this cage and clean out the latrine? Not a fun job, dangerous. So if we could reduce it. So we put the compost tea through the irrigation system. So it's just like getting a rain of these really good biology organisms on everything in here, including the dragons. The dragons' health increased. Was it from the tea being applied to all of their surfaces and them getting good biology all over their bodies? Or was it because the manure, the urine started decomposing and there weren't smells? We didn't have flies in the cage. So how long could we go between going in there and clearing out what is there, what's present? So the next slide shows you that table of information where we look at the amount of E. coli across the top, the number of E. coli, the food web organisms that were present, not a quantification, but are they there or not? And then the number of samples that were taken that we're basing this information on. You can see before the tea spray, the E. coli in that in their soil in the cage was just out of sight. We never want more than 800 E. coli, and look at the number here. It's just, oh well, no wonder there were huge problems and smells, and anaerobic conditions were terribly out of control in that latrine area. So the tea was then applied on the 1st of April, and after that, the tea was applied on March 15. By April 1st, when we went in and assayed, and this was work done through the Soil Food Web Laboratory in Corvallis, Oregon. So this is numbers from that lab. You can see there's absolutely no disease-causing organisms present. We've taken care of that problem. The food web has been fully reestablished. Nutrient cycling is happening. Decomposition is going on. No need to go in there and remove the materials in the latrine. Animals were perfectly happy about this. So April 15, May 15th, June 15th, every month through the whole entire summer, we checked, no E. coli, good food web. September 15th was the first time that we started to see a little bit of that E. coli coming back. So, okay, we've got 6 months. As long as we're putting out that compost tea in the irrigation system and we're inoculating everything, we don't have to go back in and clean up the latrine for 6 months. So how happy did that make the zoo people? The people who had to do this job could wait for 6 months before having to go in and clean it up. So yet more kinds of benefits that you can get from reestablishing the proper biology. Next slide. We can break down pesticides, herbicides, fungicides, the whole 6 yards with soil biology. So there's a lot of data starting to come out in the scientific literature showing the breakdown of these toxic chemicals. In some instances, we have to go and find the right microorganisms, both bacteria or fungi, both in many cases. For example, with the synthetic herbicides like clopyralid and imprellis. Synthetic herbicides, how intelligent is this? Because those herbicides, if they're not broken down, they're going to remain in the environment, and when their concentrations get so high, they're going to start being taken up by the plant. And now we've got herbicides inside the plants. We're seeing the same thing with Roundup, where the glyphosate is being taken up by the plants when the glyphosate concentration gets to be so high in the soil. And now that means you are eating glyphosate. What does that do to your digestive system? So we need to break down, and it sometimes is difficult to find those microorganisms when we're dealing with synthetic herbicides, but we can find them. Anything on this planet can be broken down by microorganisms, but sometimes we do have to go looking pretty hard. Otherwise, these organisms are pretty much in any good, healthy soil. So make certain that you've got a good, diverse set of microorganisms. Get those multiplied out in your compost piles. Apply them onto your soil. Make sure that the soil is good aerobic conditions. Let these organisms build structure so oxygen goes as deep as it possibly can. So water goes as deep as it possibly can and can be stored in the structure of that soil. And we will break down these toxic chemicals. Next slide. So lots of stories can be told here as well. So by repairing the soil biology, you can get the right conditions to grow the plant you want. Next slide. What does your plant need? So now we're going to talk about the successional process here. What we note is that when we're dealing with bare soil, the only thing that might be growing in here would be weedy species, very early successional plants. We have to build that whole food web, so we've got to go through and we've got to build all the way through the bacteria, the fungi, the protozoa, the nematodes, and that can take a while to get that started. We'll jumpstart this by making compost that has all of these organisms doing the nutrient cycling so that we can jumpstart to wherever it is in this successional cycle that you want to go. If you want to grow weeds, you know, there's your fungal to bacterial biomass ratio, very strongly bacterial dominated. You're going to get compaction. You're going to have high nitrate levels, which is perfect for growing the weeds. Well, if you don't want to be there, we've got to increase that fungal biomass. We've got to increase all of the food web, but especially fungi, because now we want a fungal to bacterial biomass ratio that's a bit more fungal. Still bacterial dominated, but we set the stage to grow things like bromus, Bermuda, the cole and kale crops, the brassicas. Non-mycorrhizal plants belong in this category. Not enough fungi to support a population of mycorrhizal fungi. So we want to keep building that food web, higher and higher numbers, and more strongly fungal dominated if what you want to grow are the mid-successional grass species like your lawn, like your vegetables, your tomatoes, your potatoes, your celery, your carrots, your lettuce, your cucumbers belong in this category. These are typically mycorrhizal, or in many cases what we find is that they are facultatively mycorrhizal. If the plant needs help, it will allow colonization by the mycorrhizal fungi. If the plant doesn't need that help, if it's getting all the nutrient cycling it needs from your regular decomposer or saprophytic fungi and bacteria, then it doesn't become mycorrhizal. The plant decides what it needs, and the plant knows what it needs, not us. So if you're growing row crops, late successional grasses, you're into pastures and you want the really productive organisms, equal fungal to bacterial biomass ratio. And you're going to set the stage for these to be the successful plants. No weeds, no insects, no problem fungal diseases. You walk away, let your animals graze. The plants tend to grow back much more rapidly when they've got the right biology than what you would see in conventional fertilizer-driven systems, sick, unhealthy ecosystems. From this stage of succession, we're going to go over the edge into the perennial plants, shrubs and vines and bushes, 2 times more fungi than bacteria, up to 5 times more fungal than bacterial. And yes, you've got to grow the predators to match that, so you keep the nutrient cycling going. Go on to deciduous orchard systems. You can see the fungal biomass needs to be even higher. And then in conifer old growth systems, you want to grow some Christmas trees and make some money, you're going to have to be even more fungal. Next slide, if you will. I can express this kind of information in things that maybe make a little bit more quantitative sense to people, where we're actually giving you values of what you should be seeing in your soil. 100 micrograms of bacteria to 10 micrograms of fungi are going to allow you to grow the brassicas. You go up to 500 micrograms of bacteria, 250. This is where you're going to be growing tomatoes and potatoes, your vegetables. 600 to 600, we're going to be growing a really productive pasture system. Going over the edge into fungal dominated 800 micrograms versus 500 of bacteria, you're going to be growing the deciduous trees. Your orchards, your fruit trees become highly productive, and they have the best flavor ever. Up into the conifer forest systems, probably the lowest we would ever see in a conifer forest system would be 7,000 micrograms, up to maybe about 70,000 micrograms of fungal biomass versus 700 micrograms of bacteria. Notice that the bacteria are staying pretty much about the same level by the time you get to mid-successional. It's the fungus that really changes. As we want to grow different kinds of plants, we want to balance the biology in the soil to match the needs. Luckily, the plant's going to help you out with this. When you put that tree into the system, the exudates coming out of that root system are going to give your plant, the plant's going to tell those microorganisms to get the nutrients that the plant requires. And much more fungal in the requirement to retrieve those nutrients at the concentrations that your plants require. Next slide. Basically, we're looking at what causes this succession to happen. When we're looking at addition of compost, when we're going from an agricultural field that is really depauperate, really way too low in the biology, you've got to be using inorganic fertilizers here and crossing your fingers and hoping that the diseases and the pests aren't going to wipe you out sometime during the summer. But when you're looking at only 300 micrograms of bacteria, only 5 micrograms of fungi, this is the stage set for weeds, not for good, healthy crop production. So you have to be using the pesticides. You've got to be using the inorganic fertilizers that are darn expensive. And you're out there doing something on your property all the time. What's the cost of machinery and diesel and wear and tear? So we want to switch from this situation to a more biologically driven. How are you going to do that? Well, here's our compost that we're going to be applying at 1 ton per acre. So it's bare dusting on the surface of the soil. And of course, we're going to cultivate it in, or we're going to disc that compost in. We're going to deep rip it in, whatever we need to do in the springtime before you plant. So now we're going to be getting this amount of biology is in the compost, and you can see that we are replenishing all of the beneficial organisms in here. Now look at the protozoa. The F stands, the F down there, sorry I didn't explain this. F stands for flagellates, A stands for amoebae, the good guy protozoa, and C, ciliates, is the bad guy protozoa. Where do we have lots of ciliates indicating anaerobic conditions? Well, okay, you've got compaction layers in that conventional agricultural field. When we're putting out good compost, you're going to find a few ciliates, but not many as compared to the good guys. So we're replenishing all the good guys. Notice the difference in the species of bacteria and the species of fungi as compared to the conventional system. There's like nobody at home in the conventional system. And those species of bacteria that are present, the species of fungi that are present in that conventional agricultural field are the diseases. So how are you going to get rid of them? Well, you're going to overwhelm them with good guys. You're going to make sure that soil is aerobic. You're going to make certain that water and oxygen and everything is going right. So after you put that compost on, how long do you have to wait for the biology to start to get into the balance that you want to see? Well, 2 weeks later. 2 weeks. We got the biology very close to exactly what we wanted. So this is a soil that's going to be selecting for the growth of tomatoes and potatoes and lettuce and celery and things like that. We've got the nutrient cycling going. Of course, these organisms are going to grow even more as long as you don't kill them by putting on toxic chemicals. Don't go back in until every 2 weeks here. You don't have the weeds, so why would you need to till? You don't have to be putting in the inorganic fertilizers, so why do you have to disturb the system at all? Stop working so hard. Enjoy taking a nice, pleasant walk through your agricultural fields, looking to make certain that everything's going the way it should. So the next slide. Helping you hopefully all understand what it is that we're trying to do. So let's go through a couple of case studies. So we've looked at this before, so I think we can just keep going in terms of getting the biology back into the system. When we first started working in South Africa with ZZ2, they showed us their fields, and the only 2 fields that are planted to tomato in this picture are the 2 bright green rows. So this row has been put into tomato this growing season. This row has been, this is the 2nd year in tomatoes. And look at the disease that's starting to happen in areas in this row. There wasn't even enough biology that had accumulated through 10 years of not being in tomato. They only had 1 year of good growth, and then the diseases and pests, the compaction areas start becoming overwhelming, and they didn't get a good crop. So here's the next year, 3 years ago, this was in tomatoes, but now they've planted it to sorghum, and then they just let the grasses and things come back in. They're starting to prepare fields for the next rotation. So 10 years out of tomato for 1 year's of tomato growth. And so every year they were seeing that this rotation got longer and longer and longer. So they started with 1 year in between, and then it became 2 years in between tomato crops, and then it had to be 3 years, and then 5 years, and then 6 years, and then 10 years. By the time they actually started working with us, they had to be out of tomatoes for 14 years before they could successfully grow 1 year's worth of tomatoes. Well, how do you stay alive with that kind of problem? Never ending. You've got to be finding more land. And so every year they were buying more and more and more and more farms. So we came in there, we helped them make the compost. They started putting their compost in their potting soils. This is their starting area. So in that part of their production that they were using compost, they could leave the their greenhouses open to the outside air. A lot easier, temperature control, and of course, people who are in the sterile growing conditions were just appalled. But we didn't have disease, we didn't have insect pests, we didn't have problems because the biology was present and functioning. When they actually put some of their production into the high-tech sterile greenhouses, as soon as those seedlings came out and were put into the soil, they died. So we don't have to do the rotations. We can go back in here with the proper biology and reestablish tomatoes so that all of these rows could be in tomatoes nonstop. As long as you keep looking at the biology in the soil, as long as you make certain the organisms are present, then you don't have to do rotations. Well, that drives the organic world a little bit crazy because that's one of their absolute rules. Well, we need to modify the organic regs. If you're putting good compost with these levels of diversity of all the organism groups, you don't have to go through a rotation. You can stay in your cash crop all the time. Next slide. And over there on the right-hand side, you can see, how much reduction in cost. About $200,000 per hectare, or excuse me, per 300-acre farm was the reduction in the first year that we start this conversion. I think this picture is fairly explanatory. In the springtime, this particular flowering vine was having a problem with a fungal disease. The fungus was preventing the buds from being able to open. So you can see there's lots of buds on this vine, but pretty soon this vine is going to wither and die because it can't open any of the leaves and start getting the photosynthesis. So how do you deal with this kind of problem? You go out here with an application of compost tea. The organisms in the compost tea must be present so that they will outcompete, inhibit, and consume the disease-causing fungus. So that when in the course of just a few days, it goes from really looking horrendous, it's going to die. There is no pesticide, there's no fungicide that will kill this disease-causing fungus. Put the biology on there, and you got a good, healthy vine in no time at all. We've repeated this kind of work in New Zealand a number of times, in Australia. It works when you recognize what the problem is and how easy it is to fix this problem. Pesticides won't do it. Biology will. Next slide. This is a case study from Todd Harrington on Governor's Island, and I'm probably going to spend the rest of today, this lecture, going through this. So you get me for a few extra minutes here because we had the problem with the sound. So this is Governor's Island in New York Harbor. Todd is down there in the picture, standing next to me at the end of the project. This was an island where they had army barracks that were put up in, basically, I think it was the Civil War era, barracks for enlisted people to stay in. Through World War I, they utilized those barracks, but World War II, they were getting pretty disgusting and pretty worn out. By the time the 1960s, 1970s rolled around, all those barracks were condemned. What do you do with them? So they tore all those barracks down, crushed up all of the brick and the concrete, everything was crushed up. And then these three big, well, they call them mountains, three big mountains were put together. And this is an artist's conceptualization of what these three mountains are going to look like. Maximum height is 70 feet, but when you're in New York Harbor, yes, it's a mountain. Next slide shows the start of this process. So building the hills that all this vegetation is going to go in on. So in the middle of this mound is all of the rubble, the concrete, all of the materials that were ground up and just put into this big pile. Looking across the way at the second hill, there's the hill, and you can see what's starting to grow on there. Weeds, because what's the fungal to bacterial bond mass ratio in here? There are no fungi, there are no protozoa, there are no good guy nematodes, there's bacteria. So that's the vegetation you're stuck with if you don't do something to modify that biology. So Todd was hired to do that process of bringing the ecosystems back. So they studied the ecosystems. Which ecosystems do you want? So they wanted some grasslands. They wanted native grasslands. They wanted native shrublands. They wanted deciduous forest. They want conifer forest. And so they mapped out where they wanted all of these things. But think about the fact that everything started from this. And now we're going to develop all of this biology. If you can go to the next slide, please. So Yep, the area was dirt before the start of the project. So there's no biology. What do you call this? It's dirt. You can see how rapidly erosion is starting to happen as well. What was actually comprising this material? It's the rubble in the middle of the pile, and then on top of that, they put a layer of what they called engineered soil. Soil. There's no biology in there. So you cannot call it soil. It's engineered dirt, because what that underlying layer was a mix of sand, silt, and clay, sterile material for all intents and purposes. Or if there was any biology, it was the diseases, it was the problem organisms. Now they went out and they got topsoil from a number of places. They tried to get the best stuff, but still, it was basically sterile. As soon as it started raining, look at what starts happening with respect to erosion off these surfaces. If you don't get the biology in there right away, most of this is going to wash down the hill before you ever get any plant production in there. And of course, they had some flatlands where they wanted to put in baseball diamond. So, okay, fine, we can do that as well. So next slide. The topsoil and the organic matter were brought in from off-site. So the organic material, the topsoil that was really not great biology, brought in and mixed with the compost. So next slide, I think, shows the compost. And we're making, now this shows, putting the soil out, and the biology is going to be put on top of that. So compost being spread on the surfaces, and different kinds of composts in different areas, because like this would be a native grassland, this would be a shrubland area, this would be deciduous forest. So all the different kinds of soils going out, mixing in the compost. So the next slide, I think, is the explanation of the, okay. So this is on top of that soil that had the biology in it, we're actually putting the trees. So the trees were bought from nurseries. We made sure to soak those, the roots in compost tea with the right biology and mycorrhizal fungi. The planting holes where the plants were going to go in had compost put at the bottom, and then drenched that compost and filled up that hole, the potting hole for the plants, filled it up for about an inch of compost tea, and made certain that that compost tea moved into and it was absorbed by the soil below where that plant is going to be dropped into the system. And then the plants are covered. A layer of mulch went in around those trees. I think this is before the mulch went in, so you're not seeing that mulch go on top. So making certain that those root systems will have the best chance ever to get the proper kinds of organisms around those root systems. So of course, these were deciduous trees, so we made sure that on the deciduous trees, it had a fungal to bacterial biomass ratio that was up around 5 to 100 times more fungi than bacteria. Where we're planting conifers, we made certain there was even more fungi, so that these plants would have a chance of surviving in this really horrific dirt. Shrubs going into the system, making sure we're matching what the plants require. So the next slide is different compost made for the turf in the ballpark, the native grass areas, the shrub areas, the forest areas. So different kinds of composts being made. So you can see the starting small piles where we're getting the high concentration of really good biology for each of the different systems established and growing, inoculating this material into the compost piles so we have enough tonnage of the compost to be able to do the job that we need to do out in the on site. So next slide. Brewing the compost extracts and the compost tea. So here are some of Todd Harrington's tea brewers that he was using. Geo Tea Brewer is what he liked a lot and does a fantastic job. The sprayers that were being used. So in these sprayers, good mixing inside, getting the compost extract and the teas out as rapidly as we can, so there is no loss in quality, going from where we're brewing and extracting the compost, getting the biology into a liquid form, and then they're sprayed out. Next slide should show some spraying happening. There we are. So you have to be careful that the pump on your sprayer isn't crushing and smashing and destroying the biology. So you have to be checking the equipment that you're using, and you can see applying compost tea to the surface of the shrubs. Well, and of course, some's going on the ground as well. So you're helping the soil as well as making sure that you're establishing the biology on the surfaces of those plants. And you can see the downtown area of New York City because we're out there on Governor Island, right in the middle of the New York Harbor. If you look at that first picture, the Statue of Liberty is just to the left in this picture. The right-hand side, looking at a little bit further away, looking at the slopes that we're dealing with, getting the shrubs established on the slopes, some of the trees established. So all of this is included in the study and showing how rapidly within that first year, all of these different ecosystems are being started and being successful. Next slide. Some of the native grasslands right here. So this is in 2016. So now this is a year later from the photos that we showed previously. And standing at the top of the highest hill, looking back towards, I think that's Brooklyn in the distance. And you can see the different areas again. We've got the native grasslands here. We've got the parkland, so the baseball diamond over here. We've got more kind of regular park and recs with a typical POA that you would use in parks. Shrub areas, more native grassland. So all of these different biomes being successfully reestablished, and that's amazing when you consider what these hills were built from. Next slide. Looking at some of these areas where one kind of compost was put in over here to promote the growth of the grasses, and then over here where the compost being put in is meant to promote the shrubs. So all the small little shrubs starting to grow, some of the trees that were put in there. So you can see some of these kind of edges as you go through the different growing areas. The control, no biology was applied, just kind of the normal practices that they would have used before they came in contact with the soil food web, with Todd Harrington doing this kind of work. Was just over here where you can see the weather station. Back here, the anemometer up there, the weather station here. This whole slope, you can't see it from this angle because it looks really ugly. This whole slope on the far sides failed because biology was not put in there. Where we have the biology, clearly we're not having any slope failure at all. There is no danger of losing this hillside. And so when you think of some of the recent burns that have happened in California, in Washington and Oregon, as soon as that burn is over and done with, you need to be getting the biology out here so you don't have the mudslides, you don't have the consequences of not having anything to hold the soil in place. Next slide. Just another picture from that same hilltop this year. So, sorry, just this past year. We're in 2018, Elaine. So there we are in ongoing. The project was started in 2015. So that growing season, last year, 2016, the second growing season. Here we are in the third growing season, and you can see just how lush and green and really good looking this is, even though they were suffering some reduction in rainfall in this part of the Northeast. So next slide. Just more pictures of the success. The trees are moving right along. When you think about the fact that these were planted 2 years ago, they're doing pretty well. So next slide. All the different areas. Just a reminder of where we started in 2015 and where is a slightly different angle. You can see more of the steepness of this slope in the today picture, but there is no danger of loss of this hill slope. The biology is holding it in place, and then of course the trees, the vegetation is feeding the biology to make certain that everything thrives. Next slide. More pictures of the different biomes that they're dealing with, the native grasses with some native shrubs, just the native grassland. So, all these different variables, getting the biology in there to feed the plants. It selects for the plants you want. And so you get the plants you want instead of weeds, instead of problems. Next slide. So there are a lot more case studies. We have consultants that are willing and capable of working with people on your scale program in your part of the world. So, get a hold of us. We do have the list of the consultants on the Environment Celebration website. We've just updated to our new website. So I think it's online, or it's very close to being online. I'm not sure which one it actually is. But lots more pictures. We take the success stories that each one of the consultants does, and you can look at those pictures, stories on the website and get more information. Come work with us. We'd love to help you. So back over to you, Raleigh.
Oh boy. Okay, there's one little quick thing about information you'll see at the end about how you can get a hold of Elaine. That was just a phenomenal presentation.
All right, everybody. That's the end of tonight's presentation. Thanks, everybody, for joining. We'll see you next time on Economic Action Team, and join us on our webinars. Check your emails for the next presentation.